right, well, good morning and welcome to session 9 of our U.S. Territories Water Operator Training Series. So today we're going to talk about the application of chlorine disinfection. Last session we talked about disinfection in general and how that works. And so we're going to continue that conversation today. But real quick, again, my name is Matt Ziegler. I'm a program director here at the Southwest Environmental Finance Center, where I've been working for over 20 years helping small water, wastewater utilities, reach their goals and provide safe and adequate services to the community they serve. I'm happy to help you if you have any questions. I'll go ahead and put my email address in the chat, and you can reach out to me and maybe I can help you with some of your challenges. We're part of the UNM, University of New Mexico School of Engineering here in Albuquerque, New Mexico. And this whole training series is funded by the US EPA. All right, here we are today in our 9th session, talking about application of chlorine disinfection. And so all of these training materials, they're available online on our website. You can follow this URL up here, or you can just go to our website and look under our work and find all the training links located there. And so we have both the recordings as well as the slides on this website. So today we're going to do a real quick review of what we talked about last time on disinfection. We're going to get into chlorine disinfection safety because you always have to understand how to be safe before you use a chemical. We're going to learn how to store hypochlorites, and then we're going to learn how to set up a hypochlorite disinfection system, and we're going to get into how chlorine gas disinfection works. All right, so let's review what we talked about last time. And we learned about a number of different disinfectant types. We talked about one physical disinfectant, which is UV light, ultraviolet light. And so this is an effective primary disinfectant that doesn't form disinfection byproducts, but it doesn't leave a residual in your water to protect the distribution system from contamination. And so sometimes you might have to add a chlorine residual to help protect the distribution system. We also talked about 4 different chemical disinfectant types. And so the chloramines, so that's a combined form of chlorine. And so when you do chloramination, you're adding a little bit of ammonia to water that already contains a chlorine residual. And it's not a great primary disinfectant, but it is a good secondary disinfectant that reduces the number of disinfection byproducts you might have. It provides a long-lived residual in the distribution system. So it could be good as a secondary disinfectant. We also talked about chlorine dioxide and how larger systems that are surface water might use chlorine dioxide. You remember it's generated on site, and it's good at addressing taste and odor issues found by some of those algae and other organisms that are found in surface water. We talked about ozone, which is also a chemical disinfectant that's generated on site. And it diffuses, it's bubbled through water and disinfects that way, but then it volatilizes off and goes into the atmosphere. And so it doesn't stay in the water. And so it's, again, good as a primary disinfectant, but a chlorine residual may have to be added to protect the distribution system. And then finally, we talked about chlorine, and we talked about 100% chlorine, which is gas chlorine. And then we talked about both of these hypochlorite salts. So the calcium hypochlorite, which is our powdered or tablet chlorine, and then our sodium hypochlorite, which is a liquid chlorine. So the main goal when you disinfect with chlorine is you need to reach breakpoint. So if you're doing chloramination, right, you want to be in there with that combined residual, kind of focusing on monochloramines. But when we're doing just straight chlorine with hypochlorite salts or with gas chlorine, we need to reach breakpoint. And so after breakpoint, all of your residual is going to be free chlorine residual, which is the best type of residual. When we practice breakpoint chlorination with chlorine, we want to minimize those chloramines and the combined chlorine. Okay, so we want to have a minimal combined residual chlorine and as much free residual chlorine, depending on our goals. Here's something to remember, and you should be familiar with. It doesn't show up on the WPI formula sheet, but you should know that dosage equals demand plus residual, okay? And so dosage, again, it's that total amount of chlorine that you're feeding into a volume of water. It's expressed as milligram per liter, all right? So however much you feed into that water. Now, some of that chlorine's used up, all right? It's consumed by material in the water. It's expressed as milligram per liter, that's the units, but it's not available for chlorine, or it's not available for disinfection, and it doesn't leave a residual chlorine in the water. It's not measurable. All right, and then finally, residual, that's the chlorine that's remaining after demand is satisfied. Again, the units are milligram per liter. It is available for disinfection. So remember that dosage equals demand plus residual. Whatever you feed into the water, what's used up, what's left over to keep disinfecting. You should be familiar with, again, those chlorine reactions when you add it to water. And so chlorine plus water turns into this hypochlorous acid and hydrochloric acid. All right, that hypochlorous acid further reacts and it turns into this hydrogen ion and hypochlorite ion. Now, this is important because the hypochlorous acid, it's a much more effective disinfectant than the hypochlorite ion. Both are available for disinfection, but hypochlorous acid is much more effective. And so we want to maximize our ability to have more hypochlorous acid formed than the hypochlorite ion. And so the biggest factor in that is pH. And you can see that at more neutral pHs and more acidic pHs, you get more hypochlorous acid forming. You know, at a pH of 7, you're getting over 70% of the solution is going to turn into hypochlorous acid. And so once you get up into the higher pHs, we do have some systems that run into the 8s and 9s here in New Mexico. You're going to get much more hypochlorite ion forming, and so it's not nearly as effective as a disinfectant. And these systems that are up in this range are going to have to spend more money on more chlorine to do the same job if they had a lower pH. Water temperature plays a role in disinfection with chlorine. You know, warmer water temperatures, those reactions that we just talked about are going to speed up in warmer temperatures, but also you're going to get more off-gassing of chlorine at warmer water temperatures. And so if your chlorine is stored in a warm building or a hot building, it's going to dissipate more easily in the warmer temperatures. Colder temperatures, it takes longer for those reactions of chlorine with water to occur. And so you're going to need more contact time when it's colder. It also depends on type of organism. And so, you know, definitely with the viruses, they have that hard capsid outer shell that protects, you know, their DNA or their RNA. And so it's hard for chlorine to penetrate that. So it needs more time if we're talking about inactivating viruses. It does pretty well with most microbiological bacteria, like total coliform and E. coli. But then again, with protozoans, those bigger bugs, chlorine doesn't, you know, do a super effective job with Cryptosporidium or Giardia. And so that's why our surface water systems have to filter. They have to filter out those protozoans before they disinfect. Interfering agents, so things like suspended solids, turbidity, you know, interfering agents with chlorine, you know, like hardness, all of those can affect chlorine disinfection. And then also type of residual plays a role. So what type of residual do you have in your system? And so that kind of leads us to this poll question that we want to ask. You know, what are the three types of chlorine residual? Uh, Hypochlorous acid, hypochlorite ion, or chlorine? Is it total, free, and combined? Is it dosage, demand, and total, or is it dosage, demand, and free? So, we asked everybody to take a minute to go ahead and answer this poll question. What are the three types of chlorine residual? And so when everybody answered, what we saw is a real split between all four of these, split pretty evenly. And so this is an important concept to remember is that the three types of chlorine residual are total residual, free residual, and combined residual. So everybody that answered number two, you were correct. And so let's look at that in more detail because it can be a confusing concept. So when we look at residual, total chlorine residual is always equal to combined residual plus free chlorine residual. Okay, so there's a relationship between all three of those. And so when we look at that relationship on the breakpoint curve, let's say over here on this axis, this is the total residual that we are measuring. Okay, and so when we look at that, and we look at where it comes in over here, we can see that that total residual is a combination of our combined chlorine residual and our free chlorine residual. Okay, so total residual equals combined plus free residual. And we can rearrange this equation however we want to solve for the unknown. When we do practice free breakpoint, when free chlorine disinfection, we want to make sure to get to breakpoint. Okay, so when we measure residual in our distribution system as part of the revised total coliform rule, or we measure it at our entry point as part of other rules, or if we're just doing some process control, we always want to measure for free chlorine. Okay, that's what's required by the Safe Drinking Water Act. Now, if we want to get a little more information, we would measure for both total and free, and that would let us know how much combined residual we have. And so for a groundwater system, that shouldn't vary that much, right? We don't have a ton of those precursors, a ton of those interfering agents. So we shouldn't see a big difference, and we shouldn't see too much combined residual, okay? So be familiar with total chlorine residual equals combined plus free. All right. So now we can get into chlorine disinfection safety. We've learned how it works. Now we have to understand how to use it safely before we start applying it at our system. And so the first things first, if we're in person, we always ask everybody, have you read the safety data sheet? And so we would go around and have you read all the safety data sheets for the chemicals that you work with? And you're going to get a mixed bag of answers. A lot of people have never read them. Some have read some, and then some have definitely read them. And so if you haven't read safety data sheets for the chemicals you work with, then definitely I advise you to go through them and read them. And when you read them, look out for all these different sections. And so with section one, this tells you exactly what the product is and how the company identifies that product. And so we can see that this is a safety data sheet for 12.5% sodium hypochlorite, and it's made by Univar Solutions. The second section it talks about the hazard. It's corrosive to metals and skin, and it can cause serious eye damage. It also talks about some precautionary statements and kind of how you need to protect yourself. Section 3 tells you what it's made of and the ingredients. And so it's 12.5% sodium hypochlorite, a little bit of sodium hydroxide, and then mostly water. Here are the first aid measures, and so you should be familiar with how to perform first aid on yourself or a coworker if you get exposed to it. So this is what you do if you inhale it, if it gets on your skin, if you get it in your eye, and if you swallow it. If there's a fire, what are the measures that firefighting should take? It tells you about what sort of fire extinguisher you need. It tells you that a high volume water jet is unsuitable. It talks about other specific hazards that need to be accounted for if you're doing firefighting for this chemical. It also talks about what happens if there's an accidental release. What types of PPE do you need when you clean it up? How do you clean it up? And what sorts of environmental precautions you need to take. Section 7 is all about handling and storage. And so, how to protect against fire and explosion, how to safely handle it, and how to safely store it. And so, we're going to talk about these more in depth as we go through the session today. Section 8 is exposure controls and personal protection, and this is a super important section for operators to understand how to protect yourself, how to protect your lungs, and then how to protect your hand and skin and eyes, and what sorts of hygiene measures to take while you're handling this chemical. So those are all super important. I was just at a system last week doing a sanitary survey and asked, so what sort of PPE do you use when you're mixing up this chlorine and handling it? And, really the only thing the operator was using are gloves. And so not taking any precautions for their eyes, their clothing, splashing it on their skin. And so, definitely is a concern if somebody is not taking those precautions when they handle these chemicals. Uh, Section 9 is all about the physical and chemical properties of the liquid. Can be a clear or yellowish color. Talks about pH. And so you can see with sodium hypochlorite, with liquid chlorine, it really starts off in that base pH range. And again, when you add it to water, um, it forms hypochlorous acid and hydrochloric acid. And so it actually can drop the pH of the water that you add it to, even though it starts off in the basic pH range. Section 10 talks all about stability and reactivity. So you should be familiar about what it reacts with and the incompatible chemicals that you should not store it with. And we'll talk a little bit more about this during this session. Uh, Section 11 talks about toxicological information and acute oral toxicity in lab animals. Um, Section 12 is all about ecological information and toxicity to wildlife. And you can see that their aquatic life has a very acute toxicity with aquatic life. And so that's why if you're doing wastewater treatment and you're adding a chlorine residual at the end to get rid of those E. coli bacteria, those fecal bacteria, you have to drop that residual so that when you discharge it into the environment that you do not affect the aquatic wildlife. Section 13, all about those disposal considerations that you should consider when disposing of it, how you should transport it, and other regulatory information. So yeah, make sure you read the safety data sheet for the chemicals you work with. All right, so let's talk specifically about sodium and calcium hypochlorite salts and some of those specific chlorine disinfection safety things about these. Again, they are corrosive. They start off as a base and then you add them to water and they can form the hydrochloric acid. They're reactive, okay, so they can react with things, but they aren't flammable. They're not going to catch on fire if you put a lighter up against them. And definitely, as we saw during our SDS review, they're toxic by mouth, skin, or eye exposure. And odor may not provide adequate warning. And so by the time you smell something, it may have already exposed you to enough to do some damage. All right, so hypochlorites can react explosively or form explosive compounds in the presence of a number of different interfering agents. And so ammonia, amines, charcoal, organic sulfides, acids, organics like oil, brake fluids, hydraulic fluids, pesticides, gas. And so hypochlorites are an oxidizer, right? And so what a lot of these have in common, at least with charcoal and some of these organics and things like that, they have carbon. And so when you have an oxidizer and carbon, it can, cause explosions and cause fire. And so it can happen with both powdered chlorine, like calcium hypochlorite. We're going to show an example here. Or it can also happen with sodium hypochlorite. If it comes in contact, it can cause sodium hypochlorite to release chlorine gas. And so let's look at what happens when we add calcium hypochlorite, and we're going to add a little bit of brake fluid to it and kind of see what that reaction looks like. And you can see it's not an immediate reaction. It does take a little bit of time to take place. How fast it reacts depends on conditions, but here you can see that that brake fluid is starting to um, catch on fire. Um, the white smoke that we're seeing is the release of chlorine gas into the atmosphere. And so the person that was doing this, wasn't doing it safely. And so they could have just now inadvertently exposed themselves to a bunch of chlorine gas and damaged their lungs. So the extent of chlorine poisoning, it really depends on amount of chlorine exposure. So were you exposed to a little or a lot? How close were you to, where the chlorine was released, to that point of release? How long were you exposed to that chlorine? And then how were you exposed to that chlorine, the manner? And so was it inhalation? Was it in your eyes? Was it on your skin? Was it ingestion? So the extent of poisoning is going to depend on the amount, the proximity, the duration, and the manner of exposure. So let's look a little bit about the manner of exposure. So again, skin or eye contact, that happens when it spills or splashes it on your skin or eyes when you're mixing up chemicals or you're transferring some to your day tank. You can also get high hypochlorite exposure if you have a high dose that's released into the water. Maybe your system's not working correctly and your well pump, doesn't turn on. It energizes but doesn't turn on, and so it turns on the chlorine pump at the same time, but you don't have water flow. You can have a big slug of chlorine released into the water, and then it can travel downstream and affect somebody. Ingestion, so maybe accidental exposure to food or drink. Maybe you don't label your chemical containers correctly. Somebody mistakes it for their drink and ingests it, so there's ways to ingest it, or inhalation. And so if there's a leak and you inhale chlorine gas into your lungs, and then also you can get it in your eyes, mouth, and nose contact through inhalation. So, what should your response be if you have these types of exposures? So, with skin, you want to flush with plain water for about 5 minutes. You might not realize you get it on your skin, but if you feel like a slickness to your skin, you may have gotten some chlorine on it. So, you want to flush it off. Eyes. So if you get it in your eyes, you need to take out your contact lenses. It can trap chlorine between the lens and your eye, and so flushing won't work if your contacts are still in place. And then once you're ready, flush with plain water, and you really want to do that continual flushing for 10 to 15 minutes and flush all that chlorine out. Ingestion. Now, so if you ingest it, you don't want to induce vomiting. You don't want to drink fluids. Again, when chlorine comes in contact with water and your mucous membranes and your stomach and your esophagus, you don't want to force that back up because it can just aggravate that situation and damage your esophagus and your stomach further. And really, you need to seek emergency assistance to help deal with any chlorine that's been ingested. Inhalation. So if there's a chlorine gas leak, leave the area immediately and then elevate your head above as high as you can because chlorine gas is heavier than air. And then, really, for ingestion, for inhalation, you really need to seek emergency assistance to address that. Effective exposure, and so you can see direct contact with your eye is going to do severe chemical burns. You can have severe chemical burns on your skin. And ingestion, again, we talked about if you ingest it, you don't want to vomit and cause more injury to your GI tract. Effective exposure from inhalation. Again, as soon as it enters those body areas, it's going to cause corrosive conditions that's going to damage your eyes, throat, nose, throat, and lungs. With our lungs, really they don't heal readily. And so once you damage your lungs, once that scar tissue forms, they really don't get better. And so we really need to take special precautions to reduce our exposure to chlorine gas. And we'll talk about some of those as we get into that session or that section. Um, so some specific safety considerations you should take when we deal with powdered chlorine or tablet chlorine. It really needs to be stored in cooler conditions. If it reaches temperatures greater than 100 degrees Fahrenheit, it can become explosive if there's certain aggravating conditions. When you're mixing a calcium hypochlorite solution, you always want to pour powder into water to minimize that explosion risk. Okay, so you don't want to have a bunch of powdered chlorine in the bucket and then pour water into the bucket because you can cause that powder to go up into the air, which can increase that explosion risk. So definitely you want to minimize dust, and by pouring the powder into the water, you're going to help minimize that dust. Anytime you're working with the powder chlorine, you want to use PPE, and so that's everything from a cartridge respirator to face shield, goggles, things like that. And we'll talk more about what sort of a PPE is appropriate. Um, Use resistant materials when mixing. So don't mix it in a metal bucket. Don't use a metal paddle to mix it with. And so definitely you should be using corrosion resistant materials when you mix. And then, don't do any of these things. Don't eat, don't drink, don't smoke, don't chew gum, any of those things when you handle any type of chlorine. And for the most part, when you handle any type of chemicals used in water treatment. So these are some of the types of PPE you need to use when you're handling chlorine, and really what you use depends on the type of chlorine you're working with. Are you working with a gas, or are you working with a hypochlorite salt that's liquid or powder? You might want to use chemical safety gloves, or chemical safety goggles, excuse me, splash-proof goggles that can make it so it doesn't get in your eyes. You want to use rubberized gloves. You might want to use an apron, a face shield. You want to cover your arms and legs. If you're working with powdered chlorine, solid chlorine, that cartridge breathing apparatus. And then if you're working with gas chlorine under certain situations, you really definitely need to use a self-contained breathing apparatus that has its own supply of oxygen. And so we'll talk more about what that is. So, you know, we wanted to ask you, are you using safe handling practices when you use chlorine? And so we're going to go through some scenarios and look at what's safe and not safe. And so our first question is, are your chemical containers, are they all properly labeled? And so here we can see, here is a chlorine container. It tells exactly what's in the container, when it was manufactured. We can see it's NSF suitable for use in drinking water. And then when we look over here, we have no idea what's in this tank. It could be anything. And so, we definitely don't want to see those situations where we don't know what's in the day tank. And so anytime you move solutions from the manufacturer container into, another container, it should be labeled with things like chemical type, percent solution, lot number, expiration date, date opened, date transferred. All of that information is appropriate. And so we definitely want to see things like this. And so we have systems that put a pump right on top of tanks like this, and they pull directly out of the manufacturer's tank to do their disinfection. We also want to ask, are your incompatible chemicals stored separately? And so here we have our bleach solution, our sodium hypochlorite here, and it's stored right on top of this oil. So this is some machine oil that's stored in these red containers. Again, we have an oxidizer stored on top of an organic. And so if we had a leak, perfect storm type situation where um, this leaks into that, it could cause a fire. It could cause chlorine gas to go out into the atmosphere. This is something we don't want to see. Our tubing, pumps, etc., dedicated to individual chemicals. So here we have a surface water treatment plant, and they have this line is dedicated to chlorine, and this line is dedicated to a filter aid. So this is a polymer that's used to help with the coagulation process. And so definitely we see tubes, pumps, things dedicated to individual chemicals. If containment areas are shared among chemicals or chemicals compatible, and so here we have two different chemicals. This actually is a recessed concrete well here. That's a chemical containment area if there was a leak. And so when you come along this situation, are these chemicals compatible? Well, it's hard to tell, right? Because they did a crummy job with labeling. So they failed at labeling. But when we asked the operator what was in these containers, we found out that one was an alum, again, which is a coagulant used in the surface water treatment process. And then the other was the polymer. And so definitely, these chemicals can share a containment area, but they failed on labeling. And then we also want to ask, are current safety data sheets available for each chemical used? Is it posted where you're applying the chemical? Is it easy to get to and read and review? Okay, and so definitely we want to see it. So this is a system, they posted the SDS right at the point of chemical application. So anybody could see it and anybody could understand how to work safely with that chemical. Is first aid information available? Do people know how to address, any exposures? And so if that safety data sheet is available, then those first aid measures are definitely available as well. Because as we saw, that info is right in the safety data sheet. Are there warning signs and safety information is posted within view of chemical use? And so this is right on the door of a chlorine gas room for a drinking water system. We can see that there are warning signs. We can see again, this hazard diamond down here, which is to identify the hazards associated with these chemicals that are in this room. And so definitely, they're doing that correctly. Are safety showers and eye wash stations available, accessible, and inspected periodically? And so here's an example of an eye wash station. It's right in the same room where they're applying the sodium hypochlorite. It looks accessible, and is it inspected periodically? Well, here we do have an inspection tag, but I don't see it signed off on anywhere that somebody inspected it recently. And so, every once in a while, every 6 months, every quarter, it should be inspected. This round thing up here, this cap should be taken off, and somebody needs to toggle the operation switch there. The first time that you use an eye wash station like this, you don't want it to have been installed for 6 years and nobody's used it since then, because everything in this pipe right here is going to, have sediment collected in it. It's going to have corrosion products in it. And so, if it hasn't been inspected recently and used, you're going to get a bunch of foreign material in your eye. So it needs to be exercised, every so often. Does the solution tank have a level indicator? And so, you don't really want to look directly inside a solution tank to see what's in there. So you might have some chlorine gas that comes out, maybe something on your face, like glasses or something, drops in and splashes. If you do this, you might want to wear safety goggles. Instead, what we like to see is some sort of measuring stick or some sort of marks on the tank that show what that level is. And so this system took an old tape measure that had broken. Went ahead and zip tied it right next to the chlorine tank, and every day they write down how much chlorine they've used, and they know exactly how much chlorine is in that day tank. Excuse me. Another thing we like to see is that pipes are labeled with the product name and the direction of flow. And so here um, we can see that we have two different chemicals being added. Here, those injection points are labeled. They're not labeled super well, right, with a duct tape label, but again, we know that this is the disinfectant going into this quill, and then we know that this is the anti-scalant for reverse osmosis um, going in. Actually, I think this is bisulfate, not excuse me, that's not a disinfectant. So um, makes it hard to see, so maybe not labeled super well, but we'll give them a pass for now. Here we know that this is a sodium hydroxide line, and it is labeled with the direction of flow there, so you can see that arrow. All right, so let's talk about storing hypochlorites. So as sodium hypochlorite, so as liquid chlorine decomposes, its strength weakens. And so there's a number of factors that can lead to the decomposition of sodium hypochlorite. And so age is one of the primary factors. So the older that sodium hypochlorite sits, the less effective it's going to be. Also, metals like copper, nickel, and iron can all decompose sodium hypochlorite. UV light decomposes sodium hypochlorite, so we like to keep it in a room away from UV light. Heat, as we've talked about, definitely decomposes and reduces the strength of your sodium hypochlorite, and then organic material can decompose that sodium hypochlorite. So all of these play a factor, and so we want to maximize conditions so that our sodium hypochlorite lasts as long as it can. And so the ideal temperature for that is going to be right around 60 degrees Fahrenheit, which definitely I know out here in New Mexico and other parts of the western US, our pump houses, our treatment houses get definitely hotter than 60 degrees Fahrenheit. We do have a few systems that have installed air conditioning and heating during the colder months to address that. You want to keep it away from acids and again, ammonia so that you don't have those reactive substances together. It needs to be in well-fitted airtight bottles and drums. It shouldn't be open to the atmosphere. And again, keeping it away from those UV rays is important. When we talk about storing powdered chlorine and solid chlorine like calcium hypochlorite, keep it cool and dry, okay? We don't want it combining with moisture. Label it in the original containers it came in and put on the date it was received and the date it opened. All right, that should be for any chemical you use. You should be putting on received date and opened date. And again, store away from those reactive compounds that could cause explosions or fires. So really quickly, I wanted to talk to you about something called perchlorate. And so perchlorate can form as a byproduct in hypochlorite solutions. Okay, so liquid chlorine. Uh, and so that can be a sodium hypochlorite solution that's pre-made or a calcium hypochlorite solution that you make up yourself. So perchlorate can form as a byproduct. And it's a compound that's commonly used in rocket fuel, munitions, fireworks, airbag inflators for vehicles, matches, and signal flares. Okay, and so it doesn't sound great, does it? We don't want that in our water because it can cause thyroid disease, and that can inhibit iodine uptake in our bodies, and it can also impact child brain development. And so We want to minimize perchlorate formation, and so there is a standard out there. So the American Water Works Association, um, standard B300 is their hypochlorite standard, and in it, they advise you to dilute stored hypochlorite solutions on delivery. And so if you're going to dilute down to a lower concentration, you want to do that on delivery. You don't want to let that more concentrated hypochlorite sit around and then dilute it as you need it. You want to definitely store it at lower temperatures so you don't get the perchlorate formation. And you want to keep it within that pH range that it came in. You remember that basic pH range for hypochlorites is, 11 to 13. And avoid extended storage times. And that's probably the single most, single biggest thing you can do to reduce perchlorate formation in your hypochlorites is to avoid those extended storage times. All right, so we're going to learn how to set up a hypochlorite disinfection system. So this is a liquid hypochlorite disinfection system. And so, there's a number of different pumps out there that you can use to apply a liquid hypochlorite solution to your water. And so one of those, this is a diaphragm style pump. It's called an LMI. And so anytime you see a yellow pump that's made by a manufacturer called LMI. There's other diaphragm style pump manufacturers out there. And so it doesn't just have to be LMIs. Here is a peristaltic style chemical feed pump. And so this is a type of pump that's also used in medical, in dialysis. And so, so that you do not have your body fluids in contact with a bunch of pump parts. And so instead, we have a flexible tube inside of this roller assembly. And so as this roller goes around, it pinches that tube and pushes a little bit of chlorine through. And so this is our suction side, and this is our pressure side as it goes out to our water. This is another example of a peristaltic style pump from a different manufacturer. And again, you can see in here we have our roller assembly that is pinching a flexible tube and pushing the chlorine through. Another way you can have apply a liquid chlorine solution is by generating it on site. And so we're using sodium chloride, so table salt. We're mixing it with water, we're applying an electrical current, and we're making a sodium hypochlorite solution. We'll talk a little bit more about that. All right, so whenever you start looking at applying a liquid chlorine solution to your drinking water, the first thing you want to do is make sure you have the right size pump. All right, so you don't want to make it too big, you don't want to make it too small, and so there's a few factors you need to take into account to choose the correct size pump. Okay, so here's an example of a name tag on a Stenner peristaltic pump, and there's two things I want you to look at. One is what operating pressure is it rated for? And so we see that this pump is rated to operate at a pressure up to 100 psi. So if you have system pressures that go over 100 psi, this may not be the pump for you. This is also a pretty small pump. It only is able to apply a total of 5 gallons per day. So of chlorine solution. So if it's operating at 100% capacity, 24 hours in a day, it will put in 5 gallons per day of whatever solution you're applying. So keep those things in mind. Okay, and so one of the things you need to consider is what is the flow rate of the water sources that I'm treating? Okay, and then also what dosage do I want to apply? And so where those two things come into importance is when we talk about the feed rate equation. And so chlorine purity is also a factor. And so, the feed rate, how many pounds or how many gallons per day of chlorine solution can I apply or do I need to apply? And so it's dependent on your dosage, how much you want to apply, versus how much water you're treating, what your flow rate is. This is a conversion factor to convert from gallons or pounds to gallons or gallons to pounds. And so that's the weight of water. Um, each gallon of water has 8.34 pounds in it. And then chemical purity. And so what you do is you say, okay, so I want a dosage of 1 milligram per liter. I'm trying to treat this volume of water in a day, maybe 500,000 gallons, and I'm using a 12.5% solution strength. Once you plug that in and do all of that math, then that will tell you how many pounds per day or gallons per day you need to be worried about, and then you base your pump size off of that. All right. So the other thing you also need to make sure, again, we already talked about is, what is my system pressure at the point of chlorine application? Can I overcome that system pressure? Also, you want to make sure, to look at how are you going to pump out of your day tank. And so the best way is through something called flooded suction. All right up here, this is an incorrect type of flooded suction. And so we can see that we have our foot valve in the bottom of our tank. It comes up out the top and down to our pump that sits on the floor. This is known as false flooded suction. And so in this case, you're actually creating a siphon. And so if all of our check valves in our pump and in our ejection point fail, we can actually siphon everything that's in our chemical tank into our water system. Instead, you want to have real flooded suction. And so here's an example where the pump is at the bottom of the tank and the suction lift line is at the bottom of the tank. Here's another example where you have your um, your suction line is plumbed in at the bottom of the tank. And so you always have the weight of your solution on your suction line for your pump. So you're not going to lose prime. It's the absolute best way to set up your pump, but not always easy. Instead, what we see a lot with system is our tank mount. So this is an example of tank mount. So again, we have our day tank of chlorine solution. We have our pump up on top of it, and then we have our suction lift line with a foot valve. And the previous here, you don't need a foot valve, okay? We don't have to worry about a foot valve because we have flooded suction. We don't need to keep our solution in our suction lift line as we do with these tank mount situations. And so that's what the foot valve does. It keeps solution in our suction lift line. And then we also have example of shelf mount. And so it's not on top of your tank. Instead, it's above a shelf. The main thing that we want to consider when it's a shelf mount like this is we don't want to get greater than 5 feet in height between the bottom of our pump and the bottom of our foot valve. It needs to be less than 5 feet. Otherwise, the pump's not able to overcome that feet. So make sure to keep it less than 5 feet if you're a shelf mount. Another best practices when it comes to chlorine application is that chlorine pump must be tied to flow. Okay, so here's an example over here where our chlorine pump is actually tied to our well pump through an electrical circuit. And so when the well pump energizes, it turns on the chlorine pump. But we do have limited situations where the well pump energizes, but it won't come on. And so we don't have flow. The chlorine pump's pumping away, but it's not pumping into anything that's flowing. And so you're getting a big slug of chlorine that's going into your plumbing tree at once. And so we really don't like it tied to an electric circuit. Instead, what we want to see is tied to flow. And so over here in this example, the chlorine pump is tied to a paddle switch. And so when there is flow in the pipe, that paddle switch triggers and it closes that electrical circuit, which turns on our chlorine pump. This example on the bottom again, that chlorine pump is tied to a signal output from this flow meter. And so there has to be flow in this pipe for the flow meter to send an electrical signal to close the circuit and turn on the chlorine pump. So this is what we like to see, tied to flow. And then you also need to have adequate spill containment for your chlorine solution. And so we always ask when we're in person, what does adequate spill containment mean to you? And so adequate means that your spill containment can accommodate 100% of the solution that's in the tank. And so if you have a 35-gallon tank over here, you need to have at least 35 gallons or more of spill containment. And then we always want to have a treated water sampling tap. So here's an example of one. It's a smooth nozzle, so we can't hook up a hose to it and create a potential cross connection. What this sample tap does, this one actually serves two purposes. It serves as the entry point to distribution, and so this is where chemical compliance samples are taken for like nitrate, metals, cyanide, fluoride, VOCs, SOCs, radionuclides, but it also allows you to um, investigate the how effective your disinfection process is being. Are you getting a chlorine residual here that meets your goals before it goes out to the distribution system? So this is what we like to see. Here again is just an overall diagram of everything we talked about. You can see the flow switch. You can see how this whole thing's set up. And so the only thing I don't see here is spill containment. If you want to watch our pump setup video on YouTube, you can follow this link or go ahead and scan this quick reference code with your phone, and you can see start to finish setting up a chemical feed pump to pump chlorine. All right, so the last thing we're going to talk about today is gas chlorine disinfection. It's not used a ton anymore like it used to be, but it could show up on the operator certification exam. Just because you don't use this type of disinfection, it doesn't mean that it won't show up on the exam. So you should be familiar with it. So when we talk about gas chlorine, it is a greenish, yellowish gas, just like it shows here in this flask. This is what it shows up as. One of the key properties of it is that it's 2.5 times heavier than air. And so it's going to go down to the ground and sink and displace oxygen and displace air below it. Again, like any chlorine, it turns into hydrochloric acid when it contacts moisture, right? That's that first reaction of chlorine with water. You get the formation of hypochlorous acid, which is a great disinfectant, but you also get the formation of hydrochloric acid. It decreases the pH of the water it is added to, and so just like any chlorine. It doesn't support combustion, so again, you can't hold up a lighter to it and it's not flammable. But it can react with, other substances that we've just talked about. And the way it's delivered, the way it comes in either 100 or 150-pound cylinders. It can be a 1-ton cylinder or even rail cars from 16 to 90 tons. So industrial manufacturing processes may get it in rail cars. We don't see a ton of 1-ton cylinders anymore. After 9/11, those things are more heavily regulated. And so what we really see when systems gas disinfect, we're going to see those smaller 100 to 150-pound cylinders. And it's filled as liquid under pressure. It turns to liquid, and those cylinders are going to be filled at 85% full. And then once it comes out from under pressure and at room temperature, it's going to turn into a gas. This is what a typical gas disinfection system looks at like. This is a 100 to 150-pound cylinder here. You can see it's filled 85% full. Bottom part is going to be that liquid chlorine under pressure and then the chlorine gas. It's going to travel out of that cylinder past a pressure regulating valve. And so, definitely you don't want to have it all escape at once. You want it to go out under a very controlled pressure. So that's what that PRV is for. You're going to have a rotometer, and so a rotometer is a little ball inside a tube that tells you, how much chlorine gas you're applying. And also, you're going to have a regulator to control that flow of chlorine gas. And then basically, there's an injector. As the water moves through that injector, it's going to grab the chlorine gas and put it into solution. So let's look at some more actual pictures of what this system looks like. So here's a system in operation, all right? And again, so we can see a number of different things here. We can see the rotometer here and the regulator to control that flow of chlorine gas. Um, and the system that's on here right now, this is an automatic turn-off system. So it closes that valve automatically if there's a leak. Again, we can see closer that rotometer with that regulator. And then you notice here, this chlorine cylinder also has a wrench on it. And so it's a quarter turn to close the cylinder. If everything else fails and there's a chlorine gas leak, then the system is able to have their operators put on their SCBA, go in the chlorine room, and shut off the cylinder manually. This is a chlorine injector, also called a chlorine ejector. So both terms can be correct. And so this is the flow of water. So we have let's see, so we have treated water or raw water coming in from the top, makes a turn, gets treated with chlorine gas before it goes out to a storage tank. One thing about chlorine gas is that you measure feed rate. Okay, so you measure how many pounds per day you use by putting the cylinder on a scale. Again, remember the chlorine in here is 100% chlorine gas, and so when it goes out, you can measure directly how much chlorine you're using by what's on this scale. And so over here, you can tell that exactly what that weight is. And that figures right into that feed rate equation, which is pounds per day. Here is a gas chlorine room. And so this system actually switched from using these 1-ton cylinders, so these aren't in use anymore. These are empty, hopefully, to using these 100 to 150 pound cylinders. And you can see over here we have our regulators. These are our pressure regulators. We have our rotometers with our flow regulators over here as well. You should be familiar that these chlorine gas cylinders with a Z, it should be an S, they have a fusible plug in them. And so basically what this is, it's a device that basically this plug melts and softens at 158 to 165 degrees Fahrenheit, and it releases the chlorine gas in the cylinder under controlled circumstances. So if you have a fire, you don't want that chlorine gas cylinder to cook and cook and cook in that fire until it has a catastrophic explosion. Instead, you want these fusible plugs to melt and have a controlled release of the chlorine gas. 100-pound to 150-pound cylinders typically might have just one plug, and those 1-ton cylinders are going to have up to 6 of these fusible plugs. You should be aware that there is a memo out there warning you that these fusible plugs, that space heaters can actually cause these fusible plugs to soften and melt if that space heater is kept too close to them. So if you have a space heater in your chlorination room, it really should be stored a long ways away from those fusible plugs and from the cylinder. Otherwise, you could have a release of chlorine gas that's unintended. So gas chlorine storage, cylinders should be stored upright. Okay, and they should be chained, about 2/3 to 3/4 of the way up. This one might be chained a little bit low, so if it's chained low, it'll be top heavy, and so it can topple out of that chain. If it's chained too high, then it can slide out, and so we want to make sure it's chained about 2/3 of the way up. We want to protect those cylinders from rain and weather, so they should be stored inside a room. We also want to keep them cooler, right? For a number of different reasons we've already discussed. So it should be climate controlled. We need to move those cylinders, both full and empty around, move them around with a dolly that's like this, and we want to make sure to chain them up when we're moving them around. And again, empty cylinders should be stored in a similar manner. Store them away from organics, gas, all of those reactive chemicals that we've already talked about. Also, the disinfection building should be equipped with a chlorine gas alarm, automatic. So, and you can see here that it's near ground level because chlorine gas, again, is heavier than air, 2.5 times heavier. And so you need to have that alarm system. When we talk about the chlorine gas room, it needs to have very specific ventilation setup. The light switch and the vent switch should be outside the chlorine room, so you should not have to go in the chlorine room to turn on the light switch and to turn on the vent. Again, fresh air from the ceiling. So here we have fresh air coming in from the ceiling, and then discharged air within 12 inches of the floor. And so in this case, actually, we have an air well here where the fresh air comes in, it goes into the air well. Any chlorine gas is going to go ahead and sink into this well, and then it can be discharged into a treatment system. And so if a chlorine gas leak occurs, we want to be able to funnel all that chlorine gas into a chlorine scrubber, into a treatment system. And so here's an example of a treatment system for a 1-ton cylinder inside this treatment system. And so again, this pipe here is going directly into this treatment system. And so inside this treatment system is a caustic sodium hydroxide, which will react with the chlorine gas and remove it from the air. Also, if you're doing chlorine disinfection, you need to have a standby generator, available to operate the air handling system as well as the chlorine scrubber. So chlorine gas personal protective equipment. This is an example of a self-contained breathing apparatus. It's very similar to what firefighters used, very similar to scuba underwater breathing apparatus, but it's not intended for use underwater. It needs to be located near but outside of the chlorine room. You really don't want to have to go in the chlorine room to get your PPE if there's a leak. You want to put it on, go in the chlorine room, turn off the chlorine, and make sure that exposure is limited. You also want to limit exposure for only having authorized personnel around, so you don't want to have a big tour group going through your chlorine gas room, and you want to post clear and visible warning signs. For chlorine gas leaks, a great way to check for it, maybe you've just put together the ejector or the injector, or maybe the alarm hasn't go off, but you're worried about a gas leak. You check for leaks with a 28 to 30% ammonia solution. And so here is an example of this system. They've mixed up their 30% ammonia solution and put it in this squirt bottle, which they can spray on joints and determine if there's a chlorine gas leak. It's not a super great system here because if you'll notice, they didn't label what's in the bottle. And so we have no idea that this is the ammonia solution. If there is a leak, the ammonia is going to emit a white vapor. And so that will indicate a chlorine gas leak if the ammonia solution has a white vapor associated with it. If a leak is detected, you want to immediately put on your PPE, your SCBA, and turn off the chlorine valve. And then anytime you're taking a gas chlorinator out of service, you should shut the chlorine supply off at the tank, Then let the lines evacuate of all the chlorine gas before you turn off the water. So if you turn off the water first and then evacuate the lines, you're just going to release chlorine gas into the air. So you want to make sure all that excess chlorine gas goes into the water before you turn off the gas. Before you turn off the water, excuse me. And then you want to find the leak and repair. And you can see this system here has an emergency repair kit for their system. This is, again, a summary of the gas chlorination room. So we have windows where we can observe what's going on in the gas chlorine room. We have our safety equipment nearby. We have our SCBAs located on the outside. We have our stored chlorine. We have our active chlorine cylinders here. And then we have our treatment system, our gas scrubber over here. And we have our emergency power. In case of a rapid release of chlorine gas, never enter the room without an SCBA. If the room needs to be evacuated, stand tall and hurry out. Evacuate upwind and to the highest point. If any chlorine gas vapors escape the building, if they don't make it into the scrubber, you need to notify emergency personnel, fire, and police. And so your system should have an emergency response plan in place if you are using gas chlorine for disinfection. For chlorine gas exposure, remove and dispose of your clothing, take a shower, don't induce vomiting or drink fluids, and seek emergency help. Dial 911. All right, well, that's it for today's session on chlorine disinfection, the application for sodium hypochlorite and gas chlorine. In 2 weeks, we're going to go into the third part of our disinfection series, where we're going to talk about the application of chlorine in your distribution system. We're going to learn about residual measurement and then also about evaluating and adjusting that treatment process. If you have any questions, please feel free to go ahead and email us or call us, and we'll go ahead and get those questions answered. All right. Well, thanks so much for coming today, and we hope to see you next week.